Hello everyone, today we're going to cover two exciting topics. So one is how dynamic arrays work in storage, and the other is how the memory is laid out in Solidity. Understanding those two things will help you write better code, more secure code, and be a more efficient programmer. It will also help you debug your code better and avoid any exploits. All right, let's get started. We're going to jump into the visual representation here of storage. So as we have done before, we like to think of our storage as a contiguous array of these storage buckets going from 0 all the way up to 2 to the 256 minus 1. Okay, the question is, how is a dynamic array stored in storage and how is it laid out? So we've covered mappings before, and dynamic arrays are similar, but there are some differences. So a quick recap on mappings. So the way a mappings was stored was that we had to hash the index of the bucket and the key in reverse order. In fact, the key with the index of the bucket being the storage bucket the mapping was defined in. And when we hashed that, it would give us the location of the value. So go watch the other video we have on this topic. Now for dynamic arrays, it's going to be a little bit different. So let's take a look at a code example. So right here, we have a code example called dynamic array storage. That's a contract. We have the first storage variable X. I just created that to kind of not make it super simple, but I mean, so you're just going to find 2 in the first bucket. And then this dynamic array A, okay, it's a dynamic array of uints, and this is the syntax for that, is started off as empty, right? And it's, we're going to call it A. Now, we're going to have a function here that can push a value, incoming value, to this array A, okay? And that's how it's dynamic, because we can just keep pushing elements to it. We haven't specified the size anywhere of this array. You can also do fixed sized arrays, but now this is dynamic. And then like last time, in the last video we had, we can get the storage bucket of any index, so we can kind of load that content from any of these buckets, okay? So like this bucket, that's what this index is right here. Okay, so that's the 0 and the 1. And then you can get the hash of a bucket. So we can put in any index of a bucket, say index 0 right here for the input, and we can get the hash of that bucket. All right, and I'll explain why that's needed in a second. So this is a very super simple contract. And what is the layout right now is the question. So the layout right now, well, we have this x equal to 2, and we're going to put that right here in bucket 0 first. There's a 2 sitting right here. Okay, that's x. We can write that. We can say x equal to 2. This is sitting right there. And in bucket 1, this is where A is going to start. So right here in bucket 1 is where A will start. Now, the question is, what is there? When you have an empty array, what's going to sit there is the value 0. And that's it. That's kind of how the layout is. When we call push, so when we push an element to this dynamic array, so let's say we push the value 4, what's going to happen? So what is going to happen is where A is located, which is bucket 1, this is now going to have a length of 1. So what Solidity does is it stores the length of the dynamic array in the bucket where the array is defined. So remember, for the mapping, it never had the length or anything of the mapping stored here, right? It's just always stored 0, no matter how many elements were in the mapping. In the dynamic array, which is this, Solidity will store the length of the array in the bucket where the array is defined. So again, array A sits in bucket A, in bucket 1. Okay, now, where's the value? So that's the question. Again, similar to the mapping, since we don't know how long this array will ever be, because people can keep pushing to this array ad infinitum, we don't know, like, should we store it here or here or here? And to avoid any clashes with the rest of the storage layout, we rather just kind of punt the values into this storage layout somewhere at some very high value. Okay, so what I mean is, instead of starting to put the elements like in bucket 2, in bucket 3, in bucket 4, well, since we don't know how many elements will ever be there, it could clash with some storage later on, okay? So just to be safe and to generalize this rather, what we do is we actually just put the value at the hash of the index. So you remember for the mapping, it was the hash of, again, the key with the slot or the bucket index, if you will, right? Let's call it bucket. that was where the mapping key value went under that key. And we don't have a key in a dynamic array, so all we need to do for dynamic array is just hash the bucket, okay? So we'll just hash the bucket. So what's going to happen is we're going to take the hash of this bucket, which is 1, and we're going to get some very high value, so over here somewhere, whatever that is, and that's where the value will be. That's what this function, we're going to run it in a moment in Remix. That's what this function does for us. We can get the hash of any bucket. So this hash of bucket is exactly what this is. I just need to put in the bucket index. So in this case, since the bucket is 1, we're going to hash 1, and we're going to get where the value is. So if we pushed 4, we'll see a 4 right here. And then when we push elements going forward, they'll be contiguously aligned. So they'll just be put right next to each other. We're not going to also hash this to go somewhere else. They'll just be put right next to each other, because Solidity knows the size of whatever this dynamic array is over, which are UINs. So they, UN 256. So basically they will all go into these buckets contiguously, and we're going to test that right now. So that's how dynamic arrays are stored in storage. Let's go take a look. So here we have the actual code we just took a look at, implemented in Remix, and it does the exact same as you just saw. So what we're going to do is we're going to compile this code, and that went fine. And then what we're going to do is we're actually going to deploy this code. And now that we have it deployed, again, the layout initially will be x equal to 2, and then there'll be a 0 here. So let's confirm that, because we haven't pushed anything yet. So let's get the storage bucket 0. Here there should be a 2, because we have x equal to 2 up here, right? There you go, that's 2. And then when we go to bucket 1, where the dynamic array sits, we should get a 0, because we haven't pushed anything. So that's a 0. Now we're going to push a value 4 to the array. Okay, so I just pushed a value 4. I just called this function right here. And now we're going to get the storage of bucket 1, which is where the dynamic array sits. Now this should be 1. So let's check. That is 1. Now, where's the value though? Is it in bucket 2? As I said, it's not, but let's just check. Is it in bucket 2? No, that's 0. That's not 4. All right, so where is it? Well, that's what we just said. We need to hash the bucket index 1, okay? If A is set in bucket index 2, we would have to hash 2, okay, and so on. But now it's 1. So we're going to go and hash that. And again, I have this helper function to do that for me. So I'm going to hash that. And this number here, this large number, is the index of the bucket where the value is. So this ginormous number is the index of the bucket where this sits. And we saw this in the hash, in the mapping as well. But there you go. So that's the index of this bucket. So it's, as you can tell, it's not 0, 1, or 2. This is a very large number. This just means now we can go and probe that bucket, and we can see, I wonder if a 4 is there. Hopefully it is. It should be. So there you can see there's the 4. Let's now confirm that they're contiguously stored, so that they're stored in buckets next to each other. I'm going to push another element to this array, 6. So let's go back to bucket 1 where the array sits. So what do we expect now? Well, I just pushed another element. So this bucket should now contain 2 because there are 2 elements. There you go, that's 2. Again, I still have this hash from before. I can go and look at this bucket. There should be a 4 sitting there because again, I first pushed a 4, so that's the first element. There you go. But if I go 1 bucket over to 99 here, I just move 1 bucket over, I'm gonna find a 6. There you go. So this means that the 4 sits here, the 6 sits right here, and that's it. That's how it's laid out. The more elements I push, that's fine. I can just keep pushing elements. I can also pop elements. I can remove elements as well from this dynamic array. But I just wanted to show you how it's stored. So that's how it works in storage in Solidity. Now, let's transition to topic 2. We're going to take, for the first time here, a new look at the memory layout in Solidity. So that's very helpful to understand as well. And this is going to be different than what we've done so far, because so far we've looked at only storage layouts, which was a visual way to think about it was this kind of contiguous array from 0 to 2 to 256 minus 1. And we could access any element of the storage array and we didn't have to worry about it. We could go to bucket 3 million or 8 trillion. It didn't matter. It was the same cost. It was the same ease of access. There's no problem. Memory is very different. So memory is one of the other 3 ways where we can handle data in Solidity. And from the documentation, I took this and it says the second data area is called memory, as far as Solidity is concerned, of which a contract obtains a freshly cleared instance of each message call. So this is important to note. with storage, remember that was persistent. It stayed around. Whatever we put in storage, if we called the function again, that was still around in storage. And that's in fact how we could write these helper functions as well, because after I was done pushing a value to storage, I could then, in my next function call, I could go and actually load storage content. So it stuck around. It was persistent between these function calls. In memory, that is not the case. When you're done with a function call, the memory gets cleared for the next call. So we can't probe memory the same way as we do storage. I can't do something to memory and then end the function call and then have another function that goes in and probes memory, because there's no concept of like persistent memory. As you can see, it's freshly cleared for each function call here. So memory is linear. So it will look a little bit like storage in that it's just contiguous and linear, and it can be addressed at the byte level, but reads are limited to a width of 256 bits. So this means we can't read more than 256 bits at a time. However, we can write either 8 bits or 256 bits into memory. So that's just if you're not writing a lot, you can use the 8 bits. Memory is expanded by a word, 256 bits. That's the size of a word, right? When accessing. And notice that this is either reading or writing. So what we mean by that is memory is actually expanded if you just read an element that's further away than the current size of memory. And we'll get into that. So the memory always has a size, right? It goes from 0 to whatever the largest memory bucket is that you have access to date, either written to or read from. And every time you expand that, the validators need to keep track of a larger array. Okay. So it's important to understand that it also applies to reading alone, and we'll see an example of that. So they're not talking about how much memory have you written, they're just how much have you accessed, either written to or read from. So if you read from a previously or write to a previously untouched memory word, right, then that's an access, basically. And then it's expanded if necessary, if you haven't touched it before, right? At the time of expansion, the cost and gas must be paid. So memory is more costly the larger it grows and actually scales quadratically. So that's another concept we haven't touched before, because for storage, there was no extra cost based on the index of the bucket we accessed, right? It was very costly to access a bucket, but whether we access bucket 0 or bucket 8 trillion, there's no difference. In memory, that is not the case. If you access bucket 0 in memory, like memory bucket 0 versus memory bucket 100,000, there's going to be a huge difference in cost. And in fact, the cost function is right here. Let A be the size of the allocated memory. So that is, again, how much it has been written to or read from. That's kind of the allocated. Then the cost will be 3, which is, we'll see at the yellow white paper why that is, but that's a base gas cost. 3 times this A. But then also there's going to be this second term, which is going to be A squared divided by 512. And they're going to floor it. So this just means whenever A squared is less than 512, there's going to be 0 this term. So it's only linear. So what this means is, and we can actually just take a look at the yellow paper here. So you see here, the cost of memory, the total cost function of memory of a total allocated amount A is this G memory, which is 3. This is further up in the yellow paper. Times A, again, times the size of the allocated memory, plus this A squared divided by 12, okay? And this is floored, so it only kicks in when A squared is 512 or above, okay? And then it kicks in fast, and the cost really rises fast. So we have to be aware of that, that memory is not something we can just kind of have free access to like storage in the same way, right? Okay, we're gonna look at a code example in a second. But I want to just show you, whenever you call a new function in Solidity, so you call a function, whatever it is, Solidity behind the scenes, the EVM will lay out memory for you, actually. So memory is not just going to be empty buckets to start with. There is going to be some stuff in there. It's going to be prepared for you. And you're going to start a little bit further into memory than just starting at memory bucket 0, like you do in storage. So what this means is the layout memory is like this. Solidity reserves 4 32-byte slots with specific byte ranges, inclusive of endpoints, okay, being used as follows. So what they're saying is that from bucket 0 to 3F, so this is actually just 2 buckets, like 64 bytes in total, because each bucket is 32 bytes. That's going to be scratch space for hashing methods. So when you hash something in Solidity, behind the scenes, the hashing function actually needs to read what needs to get hashed from memory. So you need to put whatever needs to get hashed into memory. And they provide this scratch space for you so that it's very easy to like hash words and whatnot very quickly, actually. So it's very useful. And then the next bucket over is going to be the currently allocated memory size. So that's basically the free memory pointer. So it just points to the memory bucket, again, into the array somewhere, where like that is the highest bucket that you have accessed so far in memory. That's going to be this second bucket. So it's kind of like a memory pointer. It points to where your currently highest access index is. And then the next bucket over is the 0 slot. So it's probably reserved for something in the future, or just leaves a little buffer just in case. So that's it. I also want to note that new objects are at the free memory pointer, and memory is never freed. Okay, again, as they're saying here, this might change the future, but it's important to note there's no garbage collector. There's no concept of garbage collecting in Solidity for memory. So once you expand, let's say you had a loop that keep allocating, an array of size 100 or whatever. As this loop goes through, you'll just keep expanding memory more and more and more, because it's not going to clear out old memory from a previous loop and then put the new memory there. Okay, so that's important to know. Okay, so let's visualize this. So again, we can visualize memory kind of like storage in that they're contiguous buckets of 32 bytes each. Okay, that's fine, but there's a big difference in, first of all, the initial layout here of how it looks for every function call. And again, for each function call, this is starting from scratch. There's no persistent memory. But also the max bucket you can go to, because of this cost, okay, which is basically A here, is the total amount of addressed memory. This actually kind of tops out at about 123,000 memory elements. This varies, that's why I have this squiggly line there, because it's not, it depends certainly on other things you're doing in the function. This bucket index will depend on the total gas you use, but you're gonna hit the total block gas limit of 30 million gas if you just were to only try to issue, 123,000 memory blocks, or if you were just trying to read, you hadn't allocated anything in memory, just literally trying to read memory at, bucket index 123,000, it will crash because this literally costs as much gas as the entire block can handle. So your program will crash, and we'll see that in a second. But notice that as your function starts, your memory layer will be like this. So it'll be like bucket 0 and bucket 1 will be the scratch space, and then you'll have this bucket 2, which will be the free memory pointer pointing to this highest access memory location. And then bucket 3 will be empty. And then here in bucket 4, index 4 rather, so it's actually bucket 5, but index 4, you will have, you will start your memory, you'll start your memory layout, and you can put whatever you want then, so, all right, so what we're gonna do now is take a look at this code down here, and we're gonna probe this, and we're gonna confirm that the memory looks exactly like this. So I created another smart contract here, you call it dynamic array, and we're just going to call it expand array, and all it does is it just sets up a new array of length, and we can then also probe memory at any location, and in any memory bucket, this is this mem index, and we can put 0, that means we're probing what sits here. We put 1, we probe what sits here, and so on. That's what this means. And we can see the code here. What it does is it sets up the new dynamic array, but in memory. That's important. So now we have the, when I said dynamic array, I meant dynamic length array. It's not a dynamic array in that we can't push to it. It can't have an undefined length. We'll get to why in a second, but it can have a dynamic length. And then we can put an element in slot 0. We can put an element in the last slot of that array, or last index of that array. And then we can actually, this function here helps us load whatever sits in memory. So again, the reason we can't have a separate load function for memory is because memory is cleared every time a new function is called. So there's no persistent memory. So we need to kind of do it as we're operating with the memory in the same function. So that's why we have this now. But this just can probe any memory bucket. Okay? All right. Now to the question, why can't we have actual dynamic arrays, meaning undefined length arrays in memory? Well, remember the reason, the reason is this. So the way the dynamic array works is that, again, we have to hash the index of the bucket that it sits in. So we have to, because we never know the total length of it, we don't know how to set aside this array early on in the buckets, because we don't know what comes after. It can clash with things that comes after. So the solution to that was just to throw it into this ginormously high bucket in storage and store there. If we did the same in memory and we tried to access this memory location, we would run out of gas, right? Very, very much so, because the largest bucket we can access is 123,000 or so, right? Give or take. So we can't do this. why can't we just start building it from the end of the array backwards? Well, we don't know how large the array is because it depends on the gas cost of the rest of your transaction. So we never know. I want to make that clear. I hope that was clear from the squiggly line. But this is not a hard limit. This is not bucket 1,2,3,000 here in general. I don't know where the end of the array is. I have no idea. It could be, technically, it could be 6. Like if I'm very gas heavy in the rest of my function, I have no idea where the end is. So don't know where the end is, and that also means that I can't. There's no high memory location that I can go to store this dynamic array and let it expand to whatever size you want. I can't do that. So there's just nothing really we can do here to implement a dynamic array in memory, at least in the current design here. So that's why you can't do it in memory, because let's say you started in 4 and you just wanted to keep dynamically like pushing elements to it into the future. Again, I don't know where this ends, first of all. I don't know if it ends at 6 or at 100,000 or at 50,000, I don't know. So that's unsafe. And second of all, I also don't know if I'm going to clash with anything else happening in memory later on. Because once I started adding to it, what am I going to do if I start clashing here? Then I'm going to need to move the whole array to after that. That's going to be very costly. So it's just not possible in the current design to do dynamic memory arrays, okay? But we can do dynamic length, by which I mean the length can depend on something at runtime, like either some function input or some other calculations you're doing in your function. At least that's helpful, but you can't just do an undefined length. All right, so I hope that was clear why we cannot do it in memory. But let's look at how this memory layout works. So we're gonna go over to Remix and we're gonna look at the memory layout. So the function here is called probe memory layout, and what we do is we initiate a new array of length in memory, importantly, and we're going to put 10 in the first element, we're going to put 4 in the last element, and then at the end we can probe the mem index location. Mem index being, if we put 0 for mem index, we're going to probe this one. If we put 3, we're going to probe this one. So what we're going to do now, the point is we're going to see how this array is laid out in memory here from bucket index 4 onwards, okay? And we're going to confirm the earlier buckets too. We'll get to this memory crash in a second. Don't worry about that right now. So what we're going to do is we're going to deploy this code, and what we're going to do is, let's just say we create a length 2 array, and we're going to put, so again, we create a length 2 array, so that's going to have value 10 in the first element and value 4 in the next element in this array. And then we're going to probe memory bucket 0. Okay, so what I'm doing here is creating an array of size 2, and I'm probing this bucket. Of course, we know this bucket is the scratch space for hashing, so there should be nothing in there. But I just want to show you, we can go through each bucket like this over and over again. So now I'm going to probe this. We're going to get a 0 back from that bucket. So there's the 0 sitting right here, even though we just created an array of 2 elements with 10 and 4. So here is definitely not where the array starts because we just found 0. And that's not where we expected either because it's the scratch space. Okay? So let's run it again. Again, we can't just probe memory statically from the side. We have to, I don't have to redeploy, but so we have to do length 2 now, but let's do memory bucket 1 now. Okay? Let's probe that location. That's also 0, again, because this is also the scratch space. Okay, you get it now. Now for 2 though, this is going to be the free memory pointer. So let's see what actually happens there. So again, we don't have to redeploy. We can just call this function again, and it'll reset the memory. It'll create the array, and it will let us probe. So now we're going to get an E0, or like an OX E0. It's hex, right? So OX E0 is, as you can tell here, is actually 224. Okay. So 224 is 224 bytes, and 224 bytes is also the same as basically 7 buckets, because you take 224, you divide by 32, it's 7 buckets. Okay. So we're going to go here, and basically what it's telling us is that we have a total of 7 buckets we're using right now. So this means we're actually using from 0 up to 6 in the indices when we run this code. Okay. So why is that? Well, that's because in these 3 buckets, that's where the array sits. And we'll see it in a second. We'll see exactly what sits here. But for now, we just know this tells us that this is pointing to, kind of like this is pointing to this bucket right here. It says that there's a total of 224 bytes allocated. So we can do this. We can point to 6. So this free memory pointer in the yellow bucket here always points to the largest accessed array or a memory array bucket. Okay, so right now it's pointing out here, and we'll find out why. Let's go to bucket 3 and probe that. So we're probe bucket 3, and we expect a 0 to be there, and there you go, there's a 0. So now we are probing this bucket. Now the question is, how is the array going to be laid out here? Okay, so let's probe bucket 4. The way we would probably expect it, I don't know if you take a second to guess, you can pause the video. All right, so, let's say, so again, we have an array of size 2, and there are 2 elements in there. We could probably guess that this bucket should probably hold the size of the array so that we know how many buckets into the future here that we can access. And then 5 is going to be the first element, 6 the next element, right? So let's confirm that. So let's go to bucket, the next bucket over here, 5. And there you go. Let's see, which bucket are we at? We're at bucket 4, actually, sorry. That's the index 4. We'll get to that one in a second. There you go. So there's a 2 here in bucket index 4. All right. So there's a 2 sitting here because we have 2 elements in, or our array is of length 2. All right. Then let's go over one more. So this is going to be the first element. So that's 10, right? So 10 in hex is A, right? And that is going to be sitting right here. So this is a 10 or an A in like OXA if you're in hex, right? And then the next element over should be our 4, right? So when we go to bucket index 6, there should be a 4. So there you go, that's our 4. So that's it. That's how it's laid out. So it's pretty straightforward. Again, because it's a fixed sized array, right? It's a fixed sized array. And again, for the reasons mentioned earlier, you can do dynamic arrays with undefined length. But at least you have a fixed size array where the length of it can be dynamic. All right, so that's how that works. Now, what we're gonna do is actually trying to see if the length of the memory array indeed is 123,000. Well, before we do that, I'm gonna show you this cost function. So remember, this is our cost function for allocating memory. And I'm gonna compare it. So, okay, we're gonna jump into Desmos. And what we have here, let me zoom in. Okay, so what we have here is, up here is this horizontal purple line is 30 million. This is the block size, or this is the block gas limit, okay, currently in Ethereum. Even after you have P1559, there's a hard limit, right? The target is 15 million down here, but if you really want to run out of gas, then 30 million is going to be your ceiling, okay? We're going to see, I plotted 2 graphs here, okay, and kind of zoom in to where they're equivalent, which will be for low values of X here. X, what is X? X is the allocated memory, the total allocated memory, and Y is your gas cost. Okay, so that's why I had the horizontal bar 30 million, because Y is your gas cost, and that's 30 million is the ceiling. But X here is the total allocated memory. So what does this mean? It's basically the number of like bytes that you've allocated. So you can see for low bytes, this is very similar. The green is just if it was linear and there's no quadratic part, like this kind of penalty function, and it would just kind of keep growing. You would pay, basically for allocating 300 bytes here, you would pay 900 and so on, and all this kind of stuff. So it would keep going. But as you see, the red is the actual amount of money you're paying. So the quadratic function, as you can tell, as we zoom out, becomes extremely aggressive. Again, this Y value is the cost, right? For any X. So had it been only linear and we could just keep linearly adding more and more memory at 3 gas per memory added, we would be able to pay only this. But so the quadratic function is actually what governs the cost. And as you can see, it pretty much go vertical very soon here. And this also means that if we zoom out again, that the total amount of gas, or like the total size of the array almost, if you will, assuming you're not using a lot of gas for other things in your transaction or in your function, is about, as you can see here, is about 123,000. You see that's the X value, 123,000 give or take, right? And then, the gas value of that will be 30 million, which is the whole block, basically. So your single transaction, there will only be a single transaction if you get very close to this, which will be your transaction. So that's just to give you an intuition of why there's 122,000 is kind of the limit. But again, also like this is not the exact limit because it depends again on whatever else you're doing in your function. So we don't know the endpoint of this memory array in general. Okay, now let us show one interesting thing here, which is the memory crash. Well, first of all, before that, let me actually just try to create now an array. Again, I was just creating of size 2. Let's create of size, let's say 10, and we can probe. I want to probe this free memory pointer now. Remember this before was E0, like this, E0, okay, which was 224, all right, which was 224 bytes. And the 224 was equal to, 7 buckets, because you divided by 32. So let me just write it like this, 7 buckets. okay? Because that's the total amount of buckets we had used to allocate this. Okay, now let's just try to do 10, okay? And we can probe storage 2, because that's where that's where the total free memory sits. So now it's going to be 1E0, which is much further ahead in the memory because we needed to allocate those 10 slots. And now we can try to make it break as well. So we can say 130,000 and just probe slot 2. It doesn't matter what we're probing. Now it should run out of gas. So as we see here, right here, the transaction ran out of gas. Okay, please increase the gas limit. All right. And the gas limit right now we've set is 30 million. I just want to make that clear. In Remix, the default is 3 million. You have to set this to 30 million to mimic the block, the current block in Ethereum. And you see here we ran out of gas. Okay, so that's because we're trying to create an array in memory that's 130,000 elements. But notice if we do this now, I just want to redeploy this. Notice that we can also make this crash and run out of gas if we just read from. Okay, again, if I haven't called this function, I'm not going to do anything to that memory and that function, and this function down here is separate, of course, in memory. Everything is cleared. But notice here, what I'm doing here is I'm using assembly, which is Yule, technically, but I am just using mload. Okay, remember when we were reading a storage value before in storage, it was sload. Now it's mload because it's memory load. And I'm going to access bucket 130,000. Okay, notice I have to multiply this index with the bucket size because you know, you need to tell it that you're actually talking about buckets here, so we do this. But anyway, this is bucket 130,000, and I'm just reading from it. I am not, in this function, as you can see, I'm not storing anything to memory, just reading from it. That will also count as memory having been allocated, right? It's going to be the same cost. All right, so now I'm going to just click memory crash. It's going to call this function. I'm just reading, and you see here I ran out of gas. Okay, so both reading and writing. Up here I was writing, down here I was reading. Both of them will make it run out of gas. So this is a way to, I guess, make a function crash. Just load from memory. Very high slot here. So that is how dynamic arrays work in storage. We covered how the memory layout is, and we covered how arrays work in memory. So thank you so much for watching. I hope you found a lot of help in this and that the examples were helpful. I hope it'll make you a better programmer. It'll help you understand Solidity much better. It'll help you write more secure and more optimized code, and it'll help you debugging when there are some issues. So thank you for watching. Like this video if you like the content, and subscribe to my channel, please. Thank you very much.